In all of our preceding topics, one thing we haven't jumped into a big detail about is, can these filters provide any sort of amplification to our signal? So all of our basic RC circuits, these are all passive components in our circuit. And while they can filter, the output of the filter is always going to be slightly less than this input. So whatever we measure across this resistor and capacitor is always going to be slightly less than what's coming out of that voltage source, because these resistors, capacitors, inductors are all going to consume some amount of energy within our circuit. And so what this means for a particular filter is that if you look at its transfer function, that the maximum value that's ever going to be up here is going to be 1. So at best, you're only ever going to get in you're only ever going to get out what you put into the circuit. So if I'm sending in a 5-volt signal and none of it is getting filtered, I'm probably going to get a 5-volt signal out. But once my filter begins to operate, that value might change to 2, 3, 4 volts, depending on the amount of filtering. What these basic RC and RLC filters cannot do is to provide amplification for signals. So if some circuit wanted to have a value of 3 up here, such that if I put in 5 volts, maybe I get out 15 volts, we're going to need additional components to provide that amplification. And as we've seen in our circuits, the main component that we use to provide amplification are op amps. And so in this series of lectures, what we're going to distinguish is between filter circuits that have just passive components, these RC components, and we're going to call these passive filters, versus new types of filters that we're going to look at that will actually have op amp components in them, and these op amps will allow us to actually amplify our signal even after it's been filtered. So let's take a look at a classic design that we saw before, that of an inverting amplifier. And so we have our source resistor and our feedback resistor, and we've seen previously that how if we have an op amp signal in this configuration, the gain is the ratio of the negative feedback resistor divided by the source resistor. And for a particular circuit, our output here is going to be G times Vs, and yes, that is a V, that is a G and not a 6. And so if we were to send through an AC signal into this circuit, so maybe our signal looked like this, and we had a gain of 2, we would get negative 2 times our signal. And so we would have a circuit that looked like that. And we would get 2 times amplification on this particular circuit. Now, what happens is if we go here and we change a bit of the circuit, and in the feedback loop, we keep this resistor, but what we add is a capacitor. So we add a capacitor in this feedback loop. Our G value now transforms to being the impedance that is up here, so the negative bit that's in the feedback loop over the impedance that's in the source. And so we will have our entire sort of Z value here, so this will be ZF, and it will still be based on our capacitor and our resistor values that go through. Now, in a soon-to-follow video, I will go through the long and torturous math of how you go about finding, well, what would be the transfer function of this circuit. So if I wanted to know the relationship between the output and the input, if this was an AC circuit, we would come up with an expression that looks like this. So it would be the negative RF over RS times 1 over 1 plus J WRF, and that's going to be the feedback resistor, CF. And so what you should recognize here is that this is just our classical gain equation for a inverting amplifier, and this ends up being our transfer function that we had for a low-pass filter. So this was the same transfer function that we had, our old H of W function, for a low-pass filter. And so what it tells us is that a circuit that looks like this, we've got 2 main parameters that we can work with. When we modify these 2 parameters, we can change the amount of gain on the filter. And when we modify these two parameters, we can change the amount of the cutoff frequency. So we have two independent parameters now that we can adjust. So in this particular design, the gain for this active circuit would end up being negative RF over RS, and then the cutoff frequency for this particular filter would be 1 over RF and then CF. And so S means it's the source resistor, and F means it's in the feedback loop. And so we have these two individual parameters that we can control in this filter. So whereas previously when we had RC filters, we could not adjust the gain and we could not adjust sort of the steepness of the circuit, now we have that ability with active filters. So let's take a look again at what happens to our inverting amplifier design if instead of putting the capacitor in the feedback loop, we were to put the capacitor into the source loop. And so instead of having a feedback capacitor, we now have a source capacitor. And we're going to get the same impact that we had before, where our impedance on the top will now be the total source impedance that we have due to these two components. And like we saw before, where putting in a capacitor allowed us to have filtering ability, putting in this capacitor is going to make this circuit here, in particular, a high-pass filter. So this is going to be a high-pass active filter. And just like before, our gain is going to be controlled by this negative RF over RS behavior, because that comes from our inverting amplifier. And our cutoff frequency is going to be, as always, 1 over RC, and this R and C are going to be the source resistor and the source capacitor. And again, for this particular circuit, we have two independent parameters that we can control. We can control the gain that comes out of the filter, and we can control the cutoff frequency for the filter, and this particular filter is, again, a high-pass filter.